Hello, this is Dr. Heidelberg, and our presentation today will deal with motors. We will follow the reference textbook by Bolton with the topics of electrical systems, including motor switches and drives. And we'll also talk about system models, mathematical definition, as well as its relationship to mechanical, electrical, fluid, and thermal. The system diagram or mechatronics includes a controller which controls plant, and the way information is being transmitted is from the controller program into the servo amplifier or the driver, which receives feedback from a sensor and sends a command to the servo motor. Then the servo motor runs the actuator or the gear train, which in turn drives the plant. There are several common configurations where servo motors are being used in automation, in mechatronics. Also, the sizing of these motors is mostly given online. And we see that the application may have ball screw indexing tables, belts of various types and configurations. The types of motion drivers and motors that we typically see in industry include hydraulic and pneumatic, which are simple structure and competitive in price. And as far as the electromechanical, the stepping motors are considered to be a competitive price with simple controller. Induction motors are also competitive price. The servo motor are mostly common in mechatronics applications, industrial mechatronics. They have high precision control, high driving force. They have good vibration control and noise control, excellent maintenance and environmental proof, and also linear motors, which are similar to rotary motors by driving linear actuators. The principle that drives the equations that relate to motors are based on Lorentz force law. This is the right-hand rule, FBI. We could usually remember that, where the thumb is pointing in the force direction, the finger is in the magnetic field, and then the eye is on a third finger. And we see over here how it applies to direct current. We have brushes and which commutate the current. The current goes from the plus sign through the coil, and the coil is going through a magnetic flux. Flux goes from north to south. And then according to the right-hand rule, we have current in one direction, flux in perpendicular direction. So perpendicular to them will have a force. Force times the lever arm will give us the torque, and that's how the torque in a motor is being generated. There are several types of motors, induction motor, where we see that the magnetic flux is being generated by winding of coils. And when we have on a stator or the armature, we have coils which interact with the flux and they generate the torque. Over here we see an example of a three-phase brushless motor. And we see over here that we have magnets on a rotor, and we have on the armature, we have coils, and the coils are over here derived in three phases such that they are simultaneously all together applying a torque, make it highly efficient. And we see the phases over here, and switching, as we'll see later, will drive them. The way to switch the electrical logic circuit is by pulses which come in from Hall effects. Hall effects will generate a signal when a magnetic flux of the magnets on a rotor will pass through them. Over here we see another example of a motor, a stepper motor. And we see over here the rotor has a magnet and the windings are on the armature, the stator. And then when we see that when we, for example, the phase 3, we charge that, then the magnet will line up with the phase. And that's when they switch the phases, the magnets will follow and the shaft of the rotor will rotate. The way motors are being constructed, as we see over here, this is a DC servo motor. So we have over here the winding here on the rotor, and they're being charged with brushes. We have the stator over here with a magnet. We have also a brake, a tachometer that gives us, senses the velocity and feeds it back to the controller. And we have an encoder which senses position. And then we have the body of the motor with the mounting frame. Here's an example of an AC servo motor, industrial. We see over here the shaft with the magnets mounting on it. Then we have the winding on the stator here. And then we have an encoder in the back. They come in various length and also frame sizes. Here's an example of a simple low-cost stepper motor. The way to determine the power of a motor, it's the multiplication of torque and rotational speed. However, as in a typical DC motor, the torque speed curve is such that when the speed is at the lowest, the torque is the maximum. And then as speed is increasing, there's more back EMF voltage, which counteract the applied voltage. And therefore, the current is being lowered through the coils, and the torque decreases. So there is an optimum over here, torque times speed, and that is the maximum power right here. The next subject is the servo amplifiers, as we saw earlier, which sometimes are being called drivers. There are several types of motors and drivers, as we saw, induction, servo, synchronous AC motor, and inductive. What's interesting to see, the most commonly used are the AC servo motors, and they can be controlled, speed, position, and torque, unlike the other ones, which are limited. The speed and control ratio is 1 into 10,000, the highest of all. Also, they can control the response frequency. The bandwidth is up to 600 hertz. Most mechanical systems are much lower than that, while all the other motors with the drivers are at much lower frequencies. The maximum torque could be 300 times the continuous torque for a very short time. They also have break resistant. By short-circuiting the coils, we can generate back EMF that actually helps to stop the motor very quickly. And their precision is the highest. You see that the accuracy is on a micron, order of micron. So that's why the AC servo motor is most commonly used in mechatronics in industry. The drivers are being driven by logic circuits and various mechatronics electrical component. We see over here the thyristor, or so-called the silicon control rectifier, SCR. A typical curve over here is shown over here, similar to the diode. However, we have a gate, and the gate current is controlling the breakover voltage. When the current is zero, it takes very high voltage to break the thyristor. And when the voltage, when the current is higher, the voltage reduces. So we see over here an example, the type of rectification that we can receive with this device. We see over here an AC source, a load, and the SCR being pulsed at the gate. And depending where we pulse it, we provide there is a very, very high resistance on a negative bias, so no current can come over here. This is why the negative is being truncated. But then on top of it, when we apply current to the gate, then we reduce the breakover frequency voltage, and then when then we allow current to go through. So this is when the light is up. When we pass it over here, the complete half sign can activate the load, and when we apply it over here with the pulse, then only quarter of it, and over here we get a smaller portion of it. So that's how we may use it in a rectification circuit. We see over here that a pulse width modulation, very common way of providing through the driver voltage to the motor. We have a pulse over here. Depending how long we keep the pulse closed, then we will generate the voltage, and the average of this is what drives the motor, the RMS. We can purchase a PWM circuit and connect it to our system. Most of the time it comes enclosed in a box with plug-and-play cables. We see over here an example that we have transistors over here with 5 volts driving a motor. So when we switch over here the Q1 and Q4 transistor, then we get a current moving in this direction, where the motor is being driven in one direction, and then if we switch Q3 and Q2, then we reverse the polarity, and the motor is being driven in the opposite direction. Another type of electronic device is the MOSFET, the most common transistor. It's metal oxide. Over here there is a metal oxide on a semiconductor. The semiconductor is being doped with electron access or with hole access. This is one which is doped with electrons, which makes it an N-channel MOSFET. And it's been designated as shown over here with the gate. And then what we see over here, then we apply a positive voltage, the holes are being repelled, and then the electrons can be conducted, and the current passes from the source. The electrons passes from the source to the drain, and the drain is being positive, and the current flows from the drain to the source. And the opposite way goes with a P channel, where the flow is of holes. Now the flow of electron turns out to be faster, so the N channel is more common, and that's how it looks for $1.91. Can be purchased and included in a circuit. Here's an example how MOSFET is being used in a circuit. We see we have over here 2 switches. This is, by the way, you click here and you see the entire presentation on YouTube. you switch this switch on, and this switch is off. And what we see here, that we have a voltage over here, but since there's no voltage across the gate, then the resistance over here of the MOSFET is very high, and therefore there's no current flow. And we see that the voltage across the MOSFET is the same as the source. There's no current flow. However, when we close this switch over here, then what happens, there is a voltage, a current flowing through these two resistors, and the voltage is across the gate. And what we see here, that the source, between the gate and the source is voltage, and therefore the current can go through the MOSFET and drive the load. And you see now that the voltage, which was 12 volt before, drops, and then the current flows. We can use this in a H circuit, H simply because you see over here that the MOSFET are mounted in an H configuration. And when we turn on these two MOSFETs, then the current flows in this direction, as we saw earlier, drive the motor in one direction. Here's when these two are being turned on, the motor is driven in the other direction. And when these two are being what they short-circuited, then we get the dynamic, so-called dynamic braking. Here's an example where we can drive a stepper motor when the voltage is being driven through, for example, a phase A by applying current to this transistor. Then this coil is being activated, and the rotor is being aligned with this coil. When this one will be activated, the number 6 magnet will be aligned, and so on and so forth, to cause the rotation with the logic circuit. Here's an example of a driver, a standard driver. We have over here the specifications, and it's also mentioned that it may be used with different NEMA sizes. NEMA stands for National Electrical Manufacturing Association. They also provide the specifications for the mounting holes and the width. For example, size NEMA size 23 step motor means that it's 2.3 inches square, which means that it is 56.4 millimeters. It's shown over here in the detailed drawing of the motor. When we're talking about the plants, then we have to many times analyze it in order to determine the requirements for the motors and the amplifiers. The modeling is done by schematic diagrams, which includes the various system parameters, like in a typical mechanical system, we have mass, stiffness, and damping characteristic. And then we have the variables that describe the performance. Here's the displacement. The derivative will be velocity, second derivative acceleration. And then the mathematical configuration equations will describe the physical phenomena. Here we see an example of a mechanical system where we have a force, applying a force on mass 2, which connected to mass 1 through damping and stiffness. The mathematical equations is shown over here. These are Newton's law. saying that the mass times acceleration of body, free body diagram of body 1 equal to the summation of forces. So when Z is in this positive direction, then Z1 times K1 will be a spring force on the opposite direction. And that is why we see over here minus K1 Z1. And then when M2 is been driven to Z2 and Z1 is also driven, then the difference of Z1 minus Z2 is a force in the opposite direction on K2. That's why we see over here Z1 minus Z2, opposite direction with a minus times K2. And similarly, the damping is going to be related to the velocity difference between Z1 and Z2. And we see over here minus B, the damping coefficients, times Z1 dot minus Z2 dot. And similarly, we write the equation for Z2 with the forcing function F. Now, to solve it, we can solve the mathematical equations, and we can also use Simulink, MATLAB, which is free for educational application. You click over here and you can download it, and very quickly an engineer could analyze and find the performance of that particular system. We see over here that these equations showing over here the second derivative of Z2 of the second device is a summation of the forcing function, and over here we see that it's also the negative summation of Z1 minus Z2 as we saw earlier, and also Z1 prime minus Z2 prime, and which is minus. So we have here, we change here the signs, and we input that as a minus. But as long as we maintain the same relationship as we saw here in this equation, then we end up on a oscilloscope. We could see the result of S2 and S1. Now, what we see in this particular example is that there are some vibrations, higher frequency vibrations, and of course, this will help us to design the parameters of the system such that the output function will be smoother, or perhaps put a servo controller that will filter out this vibration and will provide us better dynamic accuracy. When we're talking about the physical modeling of various physical systems, such as fluid mechanics, thermal, diffusion, electrical conduction, the basic functions are the same. They are second order differential equations, like we saw earlier, the Newton's law, or when we go to solid mechanics, it's a second order, the system parameter, area, and magnitudes of elasticity, and we have strains and stresses which are being related. Over here in fluid dynamics, we have fluid flows and pressures. We have thermal conductions, we have temperatures and heat flux, diffusion, we have Coulomb and charges, we have charges and capacitance, electrical conductions, we have voltage and currents. They're all related with different system parameters, and they could be solved using finite element approximation with online free sizing tool. The solution is always reduced to a forcing function with a stiffness matrix and the unknown nodal values. We see over here an example how it's being done in a equilibrium equation for a stiffness problem. It's all based on Hooke's law, which provides us a basic relationship. And then we can construct the stiffness of a single element in a matrix form, and then assemble the matrix form into a larger matrix, and then solve it using MATLAB or MathCAD to determine the unknown forces and deformations. We can also use an online free finite element analysis tool. You click on this lisafa.com, and you get up to 1,300 nodes free capabilities. You can have different configurations and find the various parameters such as natural frequency, deformations due to thermal loads or static force loads. And we can also use the system to determine the formulation of a more complex system. Like here we have a positioning system by high wind linear motor gantry. The linear motor may be operating at a very high frequency, and that may result heating. We may have to design a cooling system with a fan that will have to dissipate heat. There are deformations which may require us to add vision in order to maintain static accuracy, and that analysis becomes a very integrated part of the mechatronics system. So while the mechanical engineer may not be experts in mechatronics and AI, in all the other subjects, they should be in depth in when it comes to analyzing the mechanical portion of the system. A mechatronics team member is a key person, one which is has a very deep knowledge, the leg of the T in one subject, but has very broad knowledge in all the other elements of a mechatronic system, like electrical, software, communication, and artificial intelligence, machine learning. This completes our presentations, and we'll see more of the analysis in upcoming lectures. Thank you.